So we're given that the wall's weight is 145 pounds per cubic foot, and that the design wind pressure is 20 pounds per square foot. For moment calculations, a wind can be assumed equivalent to a point load perpendicular to the wall at the midpoint of the exposed wall. So this is the exposed wall, this 5'6" range right here. So at 2'9", that's halfway to 5'6". Let's say the wind's coming from the right. We have this wind load that's doing this, and we can, from the point of view of moment, we can assume that that's a point load equivalent to the middle. And of course, moment is like, if you're, let's say there's a diving board, but let's say it's a fairly rigid one, and you're in the pool and you jump up and you hang on the diving board and you pull down, and it's cantilevering out, there'll be a moment force this direction right there, because you're hanging on this end of the diving board. And so what we're talking about here is the moment force is going to be the force of you hanging, so essentially the weight of you hanging, times, and I know most of you guys remember this, but it's good to have a reminder, times that distance. So moment force, that's why it's much more, if you want to kind of giggle, go up to the nearest door that in the building you're in or the room you're in and push on the door, but push right next to the hinge. And it just takes a lot of pressure right near the hinge, because you're not, even if you have to push really hard to give the same torque, the same moment force around that. So anyhow, at 2'9", there's wind all the way across, but from a moment point of view, we can picture this being a point load right there. And it says ignore the weight of the ignore the weight and overturning resistance of the footing. So we're going to pretend like the footing isn't rigid to the stone wall. And so we're going to kind of focus on the moment about this point here. So the whole kind of wall might, like, the footing would stay still, but the wall would kind of tip over this way. And calculate only the moments at the bottom of the vertical portion of the wall. So we're only looking at kind of the overturning moment here, and we're ignoring the fact that if there's enough reinforcing, which is hard to get reinforcing through stone like this, but if there's enough rebar, we can kind of treat this all as one singular element, and we can all treat it as one singular element, and but in this case we can't. We're kind of treating the vertical portion as separate from the separate from the foundation, and calculate only the moments at the bottom of the vertical portion of the wall. All right, so this is a student's project from probably 20 years ago in my studio, and I thought it was, he had this kind of helical, this kind of this in his model, he didn't. It's before 3D printers, but he didn't. He had this kind of helical wind turbine, and the idea was that this house would produce its own energy from its own power from the wind, and that seemed like a really good idea at the time. It's actually, when I look back on it, it seemed like a good idea. The idea of micro wind kind of at the building has really gone away. It was really, it was as hot 20 years ago as CLT is now, or as photovoltaic, building integrated photovoltaics are now. It was just considered something that was coming no matter what. And that the wind turbines might be part of the architecture, at least in windy places. But it's such a stupid idea. It's a stupid idea from so many points of view. And the reason is because you want to put wind turbines in places that are windy, and generally where there are houses, there's just not a lot of wind. And you have to get windy, you want to be on ridges like this, and you want to be really high in the air. Because that's where the wind is. And so what happens is every time you double, it's the cube of the velocity of the wind is the power output. And so every time you double the velocity of the wind, you're actually 8xing, because 2 cubed is 8. You're actually 8xing the output, the power output. So it just doesn't make any sense to put wind turbines in places that aren't that windy, when you could be putting wind turbines in places that are windy. Plus, if you have it next to the building, there's a shadow every second going across your window and from the wind turbine, and there's the gear grinding of the gearbox, and then this is pretty controversial in the acoustics community, but a lot of people can say they can hear, and I probably believe them. I think say they can hear the wind turbines, the swoosh of the wind turbines at 1 hertz. Supposedly, we can't hear anything below 20 hertz. But 1 hertz is 1 cycle per second, and so it's about the whoosh, whoosh like that, and it drives some people crazy. And I tend to believe them because there's enough reasonable seeming people that are driven crazy by this that I've come across in my acoustics, architectural acoustics career, that I believe them. Anyhow, so we don't. It just doesn't make sense to have a distributed system, and in fact. Every time you double the, I mentioned every time you double the wind speed, like on an open plane like this, you increase the power output by 8. And then every time you double the diameter of the blade, you increase the power output by 4. So having really big blades in really windy places is definitely the way to go. And that's why, utility scale wind like this in windy places, with really big blades, is something like 5 times cheaper per kilowatt, right? So I know it's kind of romantic to think about us all making our own power right next to our buildings, but it just doesn't make that much sense. It's if you have X dollars to spend on wind, probably go invest. Go be an investor in a utility scale wind farm. Anyhow. And it's the same thing with wind from the environment on a building. Every time you double the wind speed, you increase the power output by 8. So if you have the lowest category 1 hurricane is 75 miles an hour, and the lowest category 5 hurricane is 150 miles per hour. So the 151 is not twice as big. It's actually 8 times as big, which is why if you look at any of the, it's kind of weird that we name, once we name storms, we kind of treat them the same, but really a 3, 4, or 5 are where all the damage is. And if you look at the most costly, or if you think about the big Irmas and the Marias and the Camille's and all the big hurricanes over the years, they've always been kind of 3, 4, or 5. Where they've done the damage, at least the ones that are not rain events, that are more wind events. But even Harvey, which was a rain event, I think that was when in Houston. I think that was maybe a 5 also, or 4. Anyhow, these big energy hurricanes are much bigger than medium energy or low energy hurricane. And so maybe a year ago, on one of the 40 minutes of competence, I mentioned that there are more hurricanes, and someone wrote on the chat, no, there are not more hurricanes with climate change. It's just the same number. And that was a really good point. It's true. I was speaking imprecisely. There are not more hurricanes. They're just 30% more 3, 4, and 5 hurricanes. So the hurricanes, the meaningful hurricanes are much, much more. And, of course, last year we had our first named storm hit the mainland U.S., hit from west to east in Los Angeles. So, which, by the time, if you're listening to this in a couple of years, maybe that'll be normal. If you're listening to this on Amber Book in a couple of years, but if you are listening to this live right now, in my wildest dreams, I never thought that we'd have a hurricane coming and hitting Los Angeles. So there was a report done this week, actually. I think we think of a lot of the hurricanes kind of in this area, but there was a report done maybe 2 years ago by the Times, where they looked at homeowners insurance and property insurance in Florida, and the insurers, the actuaries, just couldn't get it right. Like they couldn't figure out how they could make money because there's such a risk of a 3, 4, or 5 storm coming in. But they did a follow-up this week, which made me think it's part of the reason I did this one with the wind, where they looked, and basically there's a bunch of states nominally from Pennsylvania to Iowa. And in there, in those states, the insurance companies in aggregate are paying out more for storm damage than they're charging for they're paying out more for homeowners claims than they're charging for homeowners insurance. generally somewhere, between $1.25 and $1.50 more they're paying out than they're taking in, which of course is not sustainable in a market economy. So all those people are going to have significant increases in their homeowners insurance. And in fact, there's like one town in Iowa where like no one could get homeowners insurance because they just kept getting wiped out by these different. First, it was a tornado, and then it was derecho, and generally that's what's causing. And you say, well, there's no hurricanes here, and that's true. There really aren't hurricanes there. It's the secondary, more minor events, the kind of derecho, windstorm, hailstorm kind of thing. There's just enough more of them that their models for the insurance companies just don't make sense anymore. And so let's bring it back to our wall. So we have the wind coming from the right. And I mentioned that we're going to treat it from a moment point of view. We're going to treat it as if it's at the midpoint of the exposed portion of the wall, which kind of makes sense. And so that was 2'9" up the wall and 1'3" below the wall. So that 2'9" is halfway up this, but then the 4 foot is halfway up this plus the 1'3", if that makes sense, because we're the resultant of the wind hitting this entire face is that it's going to be halfway up the face is the resultant force, but the moment force is going to be still at that point times the distance all the way down, kind of this distance from here to here. Just in the same way I talked about hanging on a diving board. Now, that's what's pushing it over at 20 pounds per cubic foot. And so we have to resist that. We have what's called a stabilizing moment or a righting moment. I called it in this problem. I probably should tell you what the right answer was. Let's talk about that a bit. So the right answer is this first one. The overturning moment is greater than the righting moment, and therefore the design needs to be further stabilized. That's the correct answer. The next choice, the overturning moment is greater than the righting moment, and therefore the design is adequate as drawn. That should be pretty obvious to you that can't be true. If the overturning moment is greater than the righting moment, then that doesn't make any sense. Then we would have a first windstorm at 20 pounds per cubic foot. We would have a wall that was flat. And then this next one, the righting moment is greater than the overturning moment, and therefore the design needs to be further stabilized. You also should be able to intuit that that's not true. And so you may have to guess between the other two if you don't know how to do the math, which is probably okay, because there are so few. You will find questions like this where you need to be able to do structures calculations, but there are just so few of them. And structures calculations for many of us are very difficult. It may not be your best hour of studying, it may not be to focus too much on the math. But at least you should understand the concepts and know that if the overturning moment is greater than the righting moment, we have to change the design. And if the righting moment is greater than the overturning moment, we can leave the design alone. So it's kind of down to the first one and the last one. The righting moment is greater than the overturning moment, and therefore the design is adequate, or the overturning moment is greater than the righting moment, and therefore the design needs to be further stabilized. All right. So it's this one, it's the first one, and let's figure out why. So the overturning moment is in red. That's the wind coming from the left. Now, what the hell is stabilizing it? Well, because kind of intuitively, there's something stabilizing it. I mean, if I built a stone wall like that, I couldn't probably just blow on the wall and have it fall over. So there must be something stabilizing it, and that's what's blowing it over is a little bit intuitive. But what's stabilizing it actually is not very intuitive at all. What's stabilizing it is the fact that the resultant the weight of the wall itself, the resultant is in the middle of the wall, and that means that there is where the wind is turning this way. And you can kind of picture that. The weight of the wall, because it's kind of in the middle and it has 5 inches on either side of it, its force is kind of coming down the middle and it's stabilizing it the other way. So the weight of the wall, the way it stabilizes it, at least at first approximation, there are a few other things that come into play, but at first approximation, the way it's stabilized is this wall, the weight of it coming down the middle is actually creating counter moment going the other direction. And if the blue arrow is greater than the red arrow, we should be okay. In reality, that's not true. There's a safety factor of 1.5 that was not given here. But it doesn't matter because what we're going to find is that the red arrow is greater than the blue arrow. So the red counterclockwise motion is greater than the blue clockwise motion. And so in a heavy windstorm, this is quite possibly going to just tip over. So what we're going to do is we're going to figure out how much force is coming down here, and we're going to multiply that by 5 inches. And we're going to figure out how much force is coming in here, and we're going to multiply that by 4 feet. And we're going to see which is bigger. So let's start with the 4 feet one. We are told that that we have that this kind of force is 20 pounds per square foot. And we'll look at one linear foot of this and kind of just treat that as our unit. So at 20 pounds per square foot, we can multiply that by all of the wall that's being exposed to the wind, which is 5.5 feet. So times 5.5 feet. And that's going to be equal to, you can go ahead and run it out yourself in a calculator. I have found that students generally, it's one thing to watch me do it, but you won't remember it if you don't try to do it yourself, even though you can surely operate a calculator. But if you run that out, it's going to be 110 pounds per linear foot of wall, which basically means that this arrow here is 110 pounds, 110 pounds. And that kind of makes sense, right? That feels right. It would be like, the weight of a person who's very light standing on the wall. And actually, this wall is considered a cantilever from a structural point of view, which doesn't really make sense because we usually think of cantilevers as horizontal. But at the scale of the wind coming horizontally, all of a sudden the whole thing is kind of a cantilever coming out of the ground from a structure's kind of statics point of view. Anyhow, we're going to take that 110 pounds and we're going to multiply it by the distance between it and our point of rotation, which is right here. And so we get 110 pounds, and we're going to multiply that by 4 feet, and we get 440 foot-pounds. So foot-pounds is kind of a funny concept, but that goes back to pushing your door at the hinge. So if you push your door at the hinge, there won't be many foot-pounds because there's not many feet, even though there's a lot of pounds, because you have to push it pretty hard. If you push it with the same force out farther away from the hinge, you have a lot more torque at the hinge, and it's because you have more moment that you're imparting. If the whole thing was rigid, you'd be imparting moment to the hinge, and the reason you have more foot-pounds is you have more feet. So if this wall was twice as tall, we ignored the fact that we ignore that 1'3" for a second. But if it was about twice as tall, we'd have about twice as much foot-pounds. If it was twice as much wind, we'd have twice as many foot-pounds, and so forth. All right. Now we have 440. Remember that number because I have it written down, but remember it because that's really the number we're looking at. So we want to make sure that the blue is at least 440 going the other direction, so it's able to resist. And so in this case, we're given that the wall is 145 pounds per cubic foot. So 145 pounds per cubic foot. And again, we're just going to look at a 1 foot sliver, a 1 foot vertical sliver of this. So we're going to multiply that by the weight of the wall, which is not just the 5'6" above, but it also includes the 1'3" below. So that's going to be 6 foot 9 from here to here is 6'9" of wall, which is 6¾ feet. So we're going to multiply that 145, 145. Again, as always, you guys who struggle with this stuff, I have found universally, you see numbers as abstract things, and you don't remind yourself enough as to what those numbers actually mean. So 145 pounds per cubic foot, that's the weight of the wall. And we're going to multiply that by the height of the wall, which is 6.75 feet in terms of the stone part. And we're going to, that gives us the weight, but for if it was 1 foot thick, but it's only 10 inches thick, it's not 1 foot thick. So we're going to have to multiply that by 10 over 12. So 10 over 12 feet. So we're trying to get something in pounds for 1 linear foot. You know, we can multiply that by 1 foot, just like we could the other one, but that kind of goes away when you multiply by 1. But we're trying to figure out how much a 1 foot wide vertical sliver of this wall weighs, and it's 145 pounds per cubic foot times 6¾ feet tall times 10 over 12, 10 inches thick. And when you run those numbers out, you get something that rounds up to 816 pounds. Now, again, what does that mean? That's this force. That's how much we're pushing down here so that we can counter around this point, we can counter it with this. So it's 816 pounds, but we're going to, just like before we multiplied it by 4 feet, we're going to multiply it by this distance between here and here, which is only 5 inches. So we're going to multiply that by 5 over 12 feet. And when you run that out, you get 340 foot pounds. So 340 foot pounds. So that's our blue going the other direction. So again, we want our blue to be bigger than our red to keep the whole thing stable, because the red's trying to push it over and the blue is resisting that. And our red is 440 foot pounds rather. That's how much force there is going this way. Trying to tilt the whole thing over. And our blue is 340 foot pounds. That's how much force going the other way. So we don't even have to be told that we need a safety factor. Our red is bigger than our blue. So this is a wall that would need to be redesigned. Now, more commonly, although it's a bit more complex, more commonly we have a retaining wall, because the wind is pretty hard, but a more common, first of all, I would say a good number of our walls that are just unbraced, that are just sitting out there, are there because of retaining walls, but also because soil is always pushing, wet soil is always pushing on the wall. So if we have a wall here and we have some soil here, we have a kind of a triangle like this in terms of our where the force is pushing on the wall from the soil, where there's more at the bottom than at the top, and the resultant, I think, is 1/3 up. I know is 1/3 of the way up the wall. And then if we look at the seismic forces on this, it's like a reverse trapezoid. There's more at the top than the bottom. If the water table is, say, here, and we denote that's important for PA, we denote it with one of those little symbols often. And then there's also going to be some water pushing here. I think that's actually a triangle also. And then if we have anything above the soil, we may have some wind. That's what we just saw, and that's kind of a rectangle where the resultant is going to be in the middle. But anyhow, we can add those all up. And so if we kind of take that same thing again, and we have let's say we have a wall here. We can have some things happen to it that are no good. One is we can have what's called sliding, which is pretty much just what it sounds like. So in sliding, our wall kind of moves over a bit and is now here. And that's no good. We don't want that. And so one of the ways we deal with that, kind of our solution for that, is we're going to make a wall a retaining wall. And we're going to put a key here. It's called a shear key. Not all retaining walls have them, but many of them do. And it depends, of course, on how much force is pushing this way and how much friction there is in the soil between the foundation and the soil. But if there's not enough friction to kind of resist, then we're going to put a shear key, which I think you can intuit what that does. That kind of locks it into the soil. So when there's this shear force where it's pushing that way, and shear force is like shears, like scissors, where one's pushing one way and one's pushing the other right next to each other. So basically, this is pushing this way, the soil is pushing that way, and in this case, this little key here is kind of locking it in and giving a resisting force. All right, so that's how we deal with sliding. Another kind of problem is called undermining. So this is sliding. Undermining looks like this. Let's draw where the wall was to begin with. But now it's down here. And it looks something like that. And the way we deal with that is generally we have to find a way to get the water around to the other side of the wall. So water, as you know, will work its way downhill. And so the water that's on the uphill side of the wall, what we want to do is we'll put perforated pipe down here and a bunch of gravel in here. So as the water makes its way down the hill underground, it hits this kind of, what to water is pretty much an open area, because that's what the gravel is. And the water falls down, goes to a perforated pipe and goes out to daylight. And we'll have, weep holes here and maybe even some midway up that allow for the water that would otherwise be building up hydrostatic pressure behind the wall and would cause undermining. We want to deal with that by allowing the water to go around the wall. Undermining. But probably the most common and certainly the most relevant to our discussion about moments and is overturning. So overturning is kind of what we looked at before with wind, but in this case, we're going to look at it with the soil pressure. So again, we have our existing wall, and now we're going to overturn it, and so it's going to look something like this, and our soil is kind of going like this, and so we don't want that either, obviously. And the way we deal with that is generally, I'll show you. We're going to, again, these all have the same shape. This is kind of the right way to do a wall, a retaining wall, what's called a cantilevered reinforced concrete retaining wall. We have enough rebar in here that this whole thing kind of acts as one element. This part right here is called the key, the shear key. This part right here is called the toe, for obvious reasons. This part right here is called the heel, for obvious reasons. And this part here is called the cantilever. And so we have the soil up here, we have the soil down here. And the way that we kind of, to put it in the same way as before, we have this force. It's it's going to be a third of the way up. The resultant force is going to be here. Of course, there's a bunch of little ones, but the resultant force is going to be a third of the way up. And that's going to want topple this whole thing over. So it's going to all the rotation there, because it's all, we're treating it as all one big thing, the foundation with the vertical portion. It's going to be right here at the toe where the toe meets the soil. And so this whole thing is going to want to rotate this way. And we want to be able to resist it. So we need something that can go the other way. It's something that can stabilize it. And it's somewhat intuitive. You should be able to tell that there's all this weight of the soil that's going to be pressing down here. And the resultant's going to be halfway between here and here. And so that times this distance is going to be pushing, in this case, counterclockwise, and it's going to be the righting moment. So if you see and of course, there's going to be, if you see, in practice or in the exams, if you see a retaining wall, that's what it's going to look like. And of course, we're gonna have all that. We're gonna have all that. In each case, we're gonna waterproof it. We're gonna waterproof it all the way along. Right about here, all the way around. So we'll have. It's not like we have to choose beforehand whether or not we, have perforated pipe and gravel. We can have perforated pipe and gravel, and we can have a key, and we can have a heel. And between all of them, we can prevent a lot of these things from happening. We can also do it with geometry, right? So this is at the University of Virginia, and they have these serpentine snake-like walls. And you can just see if you've ever taken a piece of paper and put it, on its edge and tried to let go of your hands, it doesn't do real well. But if you curve the piece of paper and you put it on its edge, the piece of paper actually is fairly stable. And so this uses that geometry to allow for a much thinner wall than would otherwise be reasonable, given that there are winds in Charlottesville. And then this is, kind of a retaining wall, kind of a classic retaining wall with the soil behind it, providing the pressure, and it wants to, topple over, but there's some kind of there's something underneath the ground that is, or maybe it's the gravity of the thickness of the wall, gravity times the thickness of the wall, but there's something about this that's able to resist all of that. There's also something called a counterfort, which is basically it has these kind of almost like buttresses in the wall. Generally with these walls, we almost always put a ton of reinforcing bar in them. It's harder to do with masonry, although not masonry block. It's pretty easy to do with masonry block. But if it's poured in place concrete or masonry block, and sometimes masonry and sometimes brick, we can put a bunch of rebar in there that allows it. I went on a run last night just as I was preparing this, and I stopped and took a picture. This is kind of a retaining wall, but it's pretty interesting how they did this, because I saw this last night and I was like, oh, there's a retaining wall, because I was coming from this way. But then I kind of went around to the backside and realized this is slopes up. And so it probably is for most of it is probably pretty close. The elevation of the soil here on this side is probably pretty close to the elevation of the sidewalk on that side. So what looks like a retaining wall kind of is at the ends, but maybe not so much in the middle. That's not a bad way to not have to worry so much about overturning or some of these other things. So when you, on the downside, you see the slope of the soil coming up, and then it's at about the same level as the concrete pavement on the other side. Now, interestingly, and probably irrelevant to the exam, but totally relevant to your practice, a lot of times to give the stability that we need to a wall, we'll put pilasters or piers, or we'll turn corners like this. That's a bit of maybe not at the scale we normally would turn corners, but when walls turn corners or serpentine or have pilasters, that gives them extra stability from overturning. Plus, I just mentioned that, sometimes there's a toe that comes out this way, but there's a heel that goes way back in that way, right? And so a lot of times we put walls on property lines, and it's not uncommon at all for architects to not realize that there's a bunch of stuff that needs to go under the property line, or the thickness of the pier will go over the property line. And so, as you're designing your walls, keep in mind that these heels and piers and pilasters and corners and stuff like that, they often, if you're putting it right against the property line, that's actually a pretty common problem. All right, guys. Good night. Get licensed.